Welcome back. My name is Tom Dunn and I'll be teaching this module of the FRC Introduction to Java Programming. This is Module 4 where we're going to start looking at control flow statements. You remember from earlier modules we've already learned about object-oriented programming and the 4 principles of object-oriented programming. That's encapsulation, abstraction, inheritance, and polymorphism. We've learned about the different relationships between objects, the inheritance relationship, which is an is-a relationship, and both composition and aggregation, which are has-a relationships. We've learned about the difference between a class and an object, and that in Java, all non-primitive types are created on the heap. That's an important distinction that differentiates Java from some of the other languages. When we got into the structure of Java programming, we looked at a class and how to declare a class, including both the data attributes and the methods. And we've also looked at the Java statements that form the bodies of methods. And we looked at the building block of those statements, which are expressions, and how we can chain multiple expressions together using Java's rich set of operators. Now we're going to look at how we can control the flow of statements. In many cases, we do not want statements just to flow from beginning to end, one path through, and we're done. We want the code to behave differently depending on the environment. What that means in an FRC sense is depending on what joystick buttons are pressed or what mode of operation we're in, whether in autonomous or teleoperated, we may want different code to execute. So that's what we're going to look at with the control flow statements. So without control flow statements, code is executed linearly, where each statement is executed once and only once from beginning to end. When we add control flow statements, we can have certain blocks of code executed if a certain condition is true, and we can also have blocks of code executed over and over again in a loop. So let's look at the decision-making statements in a little more detail. There's the if statement, the if-else statement, and the switch statement. The if statement executes one statement if an expression evaluates to true. If that expression does not evaluate to true, it skips over the following statement. As I've mentioned earlier, there's different coding conventions that we follow. One of the coding standards that we use for if statements is we always follow the if statement with a block. A Java block is a group of statements delineated by curly braces. So even if there's only one statement after an if, we still go ahead and wrap it in a block. The reason for that may not be obvious yet, but we'll get into that a little bit later in one of the later modules. So here's an example. I have an if statement, which starts with the reserved word if. Then in parentheses, I have the expression. In this case, my expression is to invoke the isMoving method, which returns a Boolean. So that expression has to evaluate to true or false. If the expression evaluates to true, I will execute the following statement, which in this case is a Java block that contains the stop member of drive. So if the robot is moving, we're going to stop driving. If else provides a secondary path of execution when the expression for an if statement evaluates to false. So let's look at an example of that. In this example, I have a variable position and I'm initializing it by invoking the getHeight member of arm and then assigning what that method returns to the position local variable. If that position value is greater than 0.95, we're going to open the grabber. We're going to invoke the member of the grabber. Else, we're going to execute one statement if the expression evaluated to false. So if we're not greater than or equal to 0.95, we're then going to evaluate a second if statement. This if statement checks to see if the expression position greater than or equal to 0.8 evaluates to true. If it does evaluate to true, we execute or invoke the deploy member of grabber. Then we have an else clause on that if statement as well. And this one always executes the move member of arm. So if we think about that logic, if we have a robot that has an elevator mechanism that can move up and down, and when it gets to 80% of the full up position, it's going to start deploying a grabber. And when it reaches 95% of the up position, it's going to open the grabber, the gripper on the end of the grabber. So we could think of that if we're holding a bowling ball, we lift it up to the 80% vertically. When it reaches 80%, we're still moving up vertically, but we also start extending outward. And when it reaches 95%, we release the gripper and drop the bowling ball into a goal. So that's basically the logic that I'm showing here. So as you can see, we can nest these if statements quite a bit to make very complex logic. So let's look at the switch statement. The switch statement is basically a nested set of if else commands. It can have multiple execution paths based on one variable that selects which of those paths gets invoked. That selection variable can be a primitive type, an enumerated type, which I'm going to get into at the end of this module, or a string. Switch statements must have a body block. That block is delineated by curly braces. Within that block, it contains one or more stanzas, and each stanza is indicated with the case statement. The case is another reserved word. That's why it's in purple. You can also have an optional default stanza. Each stanza begins with a case statement and ends with a break statement. So that doesn't sound very clear. So let's look at an example. So here I have a switch example. At the beginning, prior to the switch example, I'm going to go grab the dial from the driver station. So I'm going to go grab the constant autonomous dial, pass that as a parameter to getDial, member of driver station, and store that in autonomousMode. Now we enter the switch statement. So we're going to switch on the autonomousMode variable. That's a primitive type. And we're going to have a Java block delineated by these two curly braces that form the body of our switch statement. Within the body of the switch statement, we have cases. You can have one or more cases. So this first case is the same as saying if autonomousMode equals 0. But in this case, I just say case 0. And this is a little bit different for Java. A case statement ends with a colon, not a semicolon. So pay attention to that. And this case statement continues until we hit the break statement. So all the statements between the case and the break will be executed if autonomousMode is 0. So if our switch is on position 0, we're going to deploy the grabber at 75%, 0.75. If case is 1, we're going to drive with a speed of 50%. 0.5 is 50%. And break. When we hit the break statement, that ends the case and ends the switch. So we're going to jump all the way down to the closing curly brace. If the autonomousMode is equal to 2, we're then going to drive at 100%. 1.0 is 100%. And hit the break. The break jumps to the end of the Java block for the switch statement. Lastly, we have a default case. If we have any other value other than 0, 1, or 2, we're going to invoke the code in the default case. And that tells the robot drive to stop and then end the switch statement. So you can see a switch statement is a little more concise than writing a whole bunch of nested if, else if, so on and so forth. So let's look at loops. Loops execute Java statements repeatedly. Each iteration through the loop evaluates an expression to decide whether or not we should stay in the loop or exit the loop. The loop exits when the expression evaluates to false. The loop continues through another iteration if the expression is equal to true. And there's a couple different kinds of loops. The most common two that you're going to see in your FRC programming are the for loop and the while loop. And we've already gone over the for loop in earlier modules. There's also a while do loop, and there's recursion. Recursion is when a method invokes itself. So that is a complex form of looping that's beyond the scope of this Introduction to Java programming course. but I encourage you to read about it on your own. It can create some fascinating capabilities and interesting mental exercises to understand what's going on. So the while loop is a precondition loop. What it does, it starts with the reserved word while, which is followed by an expression in parentheses. So just like an if statement is followed by an expression in parentheses, a while statement is followed by an expression in parentheses. Then there's the loop body, which is the statement that immediately follows the while and its expression. Just like with the if statement, the coding convention is that we always follow a while with a Java block, which is wrapping everything inside curly braces. Now let's look at an example. In this while loop, we're going to evaluate the expression is enabled and is operator control. Expressions are evaluated from left to right. So we evaluate the left-hand value of this AND operator, this logical AND, by invoking the is enabled. If it returns false, we skip over the loop body and we don't even evaluate is operator control. If it evaluates to true, because we have a logical AND, the right-hand value must also evaluate to true. So now we'll invoke is operator control and see if that returns true or false. If it also returns true, then we'll enter the loop body and we'll invoke the delay member of timer, passing it a timer delay constant. Then we'll invoke the feed member of getWatchdog. This is a little bit interesting. GetWatchdog itself is a method. So we're actually invoking the feed member of the object reference that's returned by this method. So getWatchdog is a method that's invoked, and it has to return an object reference, and then we're going to invoke the feed method on the object that it returns. So this is another way of chaining expressions together to get more complex behavior. Once we've done that, we hit this close curly brace. But because this close curly brace delineates the end of the while loop's body, we're going to go back up and reevaluate is enabled, and if and only if it's true, we're then going to reevaluate is operator control. If both of those are true, we'll execute the loop again. Then we'll loop back up, we'll evaluate the two expressions, then execute the method body if they're true. Eventually, either one or the other of these two conditions in this logical AND are going to return false. When they return false, we're going to skip over the loop body and continue execution with the method immediately following the while loop body. We call this a precondition loop because we evaluate the conditions pre or before we invoke the body of the loop. So if either one of these returns false the first time we reach this while statement, we will never invoke the body of the loop at all. It'll never enter the loop body at all. If we look at the do while loop, the do while is a post condition loop. And if we look at the syntax, it kind of looks like a post condition. In this example, we have the reserved word do followed by the loop body, which again, with a loop, we always wrap the loop body in a Java block. Then we have the actual statements that form the body of the loop. And then we have a while statement with the condition at the end of the loop. So what this means is we're going to enter the loop. We're going to call process iteration, passing it count, which initially has been initialized to 0. And then we're going to increment count using the post increment operator. Then, after the loop body is invoked, we're then going to check to see if count is less than 11. If it is, since right now it's 1, it started as 0, it was incremented to 1, 1 is less than 11, so we're going to come back to the do statement, enter the loop's body a second time, invoke process iteration, passing it 1, increment count to 2. 2 is still less than 11. We're going to go back and run process iteration, passing it 2, and make count 3. And so on and so on and so on and so on and so on. Eventually, we're going to call process iteration when count is equal to 10. We're going to increment count to 11. Now, is 11 less than 11? No, it isn't. That's a false statement. So once this expression evaluates to false, we then exit the loop and continue on with the next line of code after the while statement. This is a post-condition loop because we always execute the loop body at least once. Even if the condition is false for the very first iteration, we have still executed the loop body at least once. So that can be handy for some conditions. Now let's look at the for loop. I've already gone over the for loop a couple times now, so this should be a review. The for loop iterates over a range of values. It takes three different expressions separated by semicolons: the initialization expression, the termination expression, and the increment expression. The initialization expression is evaluated once before the loop begins, once and only once. The termination expression is evaluated before each iteration of the loop body, and the increment expression is evaluated once at the end of each iteration of the loop body. So here's an example. For int I equals 0, I is less than 10, I plus plus. So those are my three expressions. Int I equals 0 is the initialization expression. That's invoked once at the beginning of the loop. Interestingly, we can actually declare new variables inside of this initialization expression, and I've done that right here. So this variable I only will exist within the scope of this loop. The scope of this loop is delineated by these two curly braces. It is the statement body. The termination expression is I is less than 10. As long as this evaluates to true, we stay in the loop, just like we did with a while loop and a do while loop. Lastly, we have the iteration expression, and in this case I'm using I++, which is the post-increment operator on I. So the first time when we hit this for loop, we create a local variable I, we create a stack frame and push it onto the call stack with that local variable I, and initialize it to 0. Then we evaluate the termination expression. We always evaluate that at the beginning of every iteration through the loop. So it kind of functions like a while loop. It's a preconditioned loop. Right now, I is 0. 0 is less than 10. That's a true statement. That evaluates to true. So we enter the loop body. At the curly brace, we're going to print out, system.out.println is a print statement. We're going to print out the literal string iteration : space and then I. So we're going to print out iteration : 0. When we get to the end of the loop body, delineated by this closed curly brace, then we go back and run our increment expression, which is I++. So I is now 1. Then at the beginning of our second iteration, we check the termination expression. Is I less than 10? Yes, it is. 1 is less than 10. So we're going to print out iteration : 1. Then we go to our termination expression, our increment expression. I is now 2. 2 is less than 10, so we'll print out iteration 2. And we'll keep doing that over and over and over and over again. Eventually, we're going to print out iteration : 9. At this closed curly brace, we're going to evaluate our increment expression, which increments I to 10. Then at the start of the next iteration, we check to see if I is less than 10. 10 is not less than 10. That's now a false statement. When that expression evaluates to false, we skip over the loop body and continue execution with the statement that follows the end of the loop body. So the for logic can get a little bit cumbersome and ugly when you're iterating over collections. Collections are outside the scope of this Introduction to Java course, but you've been introduced a little bit to the array when we talked about the main method. That's the public static void main that takes an array of strings called args. So we'll look at this example. We're looking at a method. The method's name is sum. It returns an integer, and it takes an array of integers named a. So we always read starting with the identifier. In this case, that's a. A is an array of integers. We then initialize a local variable inside the call frame of the sum method called result. We initialize it to 0. Now the syntax is a little bit different when we're dealing with collections. we say int I colon a. You read that as for each integer I in the collection A. Since A is an array of integers and an array is a collection, we're going to iterate through each and every integer in the array, and we're going to add its value to the local variable result. So result is summing up all the contents inside the array. Like I said, I encourage you to go to the Java tutorials online and read about for each loops, because it's very, very powerful when you do have a collection. In my experience mentoring students in the FRC contests, I have not seen a lot of use of collections. Every now and then you'll see collections, especially with vision processing. But for the most part, the control systems don't use a lot of collections. So we've introduced a couple of the branching statements. Branch statements alter the flow of execution within loops or within methods. So we've already looked at the break statement when we were talking about switch. Break halts execution of the innermost loop or the switch case stanza. You can also have labeled break statements, which can halt nested inner loops, but that's outside the scope of this Introduction to Java course. The continue statement immediately ends the current iteration of a loop and goes back to the beginning of the loop. The return statement exits the current method, regardless of how deep it is in nested loops, if-then statements, switch statements, or anything. So as soon as you hit a return statement, you return. If the method is declared to return a value, return has to be followed by a value to return. If the method is void, return is just followed by a semicolon. It doesn't have to include any value. So let's look at an example using continue. This is a method called fizzbuzz. So fizzbuzz is a method that has a void return type. It doesn't return anything, and it's declared public. It takes no parameters, and we can see the open curly brace here lines up with the closed curly brace all the way down here. So that declares the method body. Inside the method, I have a for loop. For int I equals 1, so we're starting at 1, as long as I is less than or equal to 100, and we're incrementing I by 1 each iteration through the loop. So I is going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 100. And inside the for loop, again, we have a Java block delineated by this open curly brace and this closed curly brace all the way down here. Inside the loop, we see we have an if statement, which has its own nested Java block, another if statement with a Java block, a third if statement with a Java block, and finally system.out.println I. So what is this method going to do? It's using the modulus operator, which is looking for the remainder of a division operation. So I modulus 15, if it's equal to 0, that means I is evenly divisible by 15 with no remainder. We're going to print out fizzbuzz and continue. When we hit continue, that skips to the end of the current loop. Since we're in a for loop, that skips over all these statements to this curly brace down here. It then returns up to the increment expression, I++, so I goes from 1 to 2. Then we check to see if I is less than or equal to 100, which it is, and we enter this again. So what is this going to print out? When I is 1, I is not evenly divisible by 15, so it skips that if statement. I is not evenly divisible by 3, so it skips that. It's not evenly divisible by 5, so it skips that. And it prints out system.out.println I, so it prints out 1. Increment I to 2, 2 is less than 100. 2 is not evenly divisible by 15. It's not evenly divisible by 3. It's not evenly divisible by 5, so it prints out 2. We increment I to 3. 3 is less than 100. That's a true statement. It's not evenly divisible by 15, but it is evenly divisible by 3. So we print out the word fizz and continue. That skips over all the rest of the statements in this for loop. We come up to our increment expression, so I is now 4, and so on and so forth. So we can see this method is going to print out 1, 2, fizz, 4, buzz, fizz, because 6 is evenly divisible by 3, 7, 8, fizz again, because 9 is evenly divisible by 3. Then it's going to print out buzz. Then it's going to print out 11, fizz, 13, 14, fizz buzz. Because when we get to 15, 15 is evenly divisible by 15. So we'll print out fizz buzz, and then the continue skips over everything else. Then we'll print out 16, 17, and then we'll print out fizz, because 18 is evenly divisible by 3. Then we'll print out 19, then we'll print out buzz, because 20 is evenly divisible by 5. So you can see this is a little bit of a nonsense method, but it shows some of the power of the continue statement. Enumerations. Enumerations are going to wrap up this module. Enumerations are extremely powerful, and I like to use them a lot in the FRC programming. An enumeration is a class. Remember, in Java, everything is a class. An enumeration is a class that defines a set of predefined constant values, and a variable that has a type of that enumeration class will always be one of those assigned values. So here's a real simple example. I have a class gear, which is an enumeration, and it's public. The declaration of the class is delineated by curly braces, as they all are, and it contains a list of values, low gear and high gear. The list is delineated with commas, and it ends with a semicolon. So if I create a local variable of type gear, that'll be an object reference, because gear is a class, and classes create instances of objects on the heap. So if I create a local variable of type gear and initialize it with a reference to a gear object, that gear object has to be either low gear or high gear. It can have no other value. Another interesting thing, each one of those values in my gear class is itself an instance of the gear class. So that's powerful. I'll get to that in the next slide. But first I want to point out a few things. The position that a value holds in the list carries absolutely no meaning. There's no numerical representation. So I can't say that low gear is a lower value than high gear, or greater than, or equal to. Well, I can compare equality. I can check to see if a gear is equal to. The reason I can do this is because the values in the gear enumeration are singletons. So what is a singleton? A singleton means Java guarantees one and only one value will exist. Remember, a gear is a class, and when I create an instance of a class, I create an object on the heap, and I get back the address of where it's located in memory. If I do any comparisons using reference objects, I'm going to compare the address in memory, because that is the value of a reference. But since Java guarantees that a singleton has only one and only one value, that means every instance that points to low gear will have the same address. So I can use the equality operator with enums. That's the only place where I can use the equality operator with an object reference, and it does what you would think it would logically do. So I can say a local variable position equals gripper.getGear, and then I can use in an if statement, if gear position equals low gear, then do some code. Or if gripper position equals high gear, do some other code. You can also use enums in a switch statement because of that singleton property. So the singleton property is very, very important. So I've already mentioned this. An enum is a class. In Java, everything is a class, so that makes it easy. But what can you do with a class? Classes can have attributes. Classes can have methods. Remember, on the last slide, I pointed out an enum has a list of values that are all constant. Because they're constants, you can only have getter methods. You cannot have setter methods or mutator methods, because those change the value, and these are constants. But you can have getter methods. You can also have constructors. A constructor is a special method whose job is to initialize a new object when it's created. Every enum class attribute is added to every single enum value, and that allows us to provide explicit meaning two values in an enumeration. So the position in the list has no explicit meaning, but we can define our own explicit meaning. So let's look at a complete enum class that actually you'll probably see something fairly similar when you actually start doing FRC programming. So here's my enum, Canassignment. Can is an abbreviation for Control Area Network. So it is an enum, it is public, it starts with this curly brace, and it ends with this curly brace down here. The first thing you generally find inside of an enum is a list of the values. So front left drive, front right drive, rear left drive, and rear right drive. And the list elements are separated by a comma, and the list ends with a semicolon. So this enum has 4 possible values. It also has an attribute, CanID, which is an integer, which is private. It also has location, which is an attribute of type string, which is private. What happens when I make my local attributes private? That's an example of encapsulation, one of the 4 principles of object-oriented programming. The only way anyone can get at those values is to go through public methods that I provide. So I'm going to skip over the next method and look at the last 2. I have a method, getCanID, which returns an integer, and it's public. And it returns the CanID. What is CanID? That is the local attribute in the current instance that this method is invoked on. Remember, every non-static method has an implied parameter, which is the reference to itself. It's called the this reference. The last method, getLocation, is a method. It returns a string, and it is public. And inside its method body, since it returns a value, it has to have a return statement. The return statement has to be followed by an object of a compatible type. And in this case, it's returning the location member of this, which is the local attribute up here, the private attribute. Lastly, we have a constructor. I know it's a constructor because its name, Canassignment, is identical to the name of the class, and it has no return type whatsoever. But it's private. What does it mean when the constructor is private? That means you can never create an instance of this class. And that's what we want in an enum, because in an enum, there are only the values defined in our value list at the declaration of the class. And those values are singletons. There's one and only one value of each one of those 4, which means we would never want to create any additional Canassignment values. Every instance of this enum has to have a reference to one of those 4 values. That's what an enumeration is. And if we look at how we declared this constructor, it takes an integer parameter and it takes a string parameter. Because we provided one constructor, the Java compiler will not create one for us. Remember, way back in an earlier module, when we were looking at classes, I said every single class has a constructor. If you do not provide one, Java will make one for you, which is a default constructor. In this case, I did provide one. So Java will not make one for me. So the only constructor this class has is my private constructor, which takes 2 parameters. And you can see it sets the CanID member of this equal to the ID parameter, and it sets the location member of this to the location parameter, to LOC, which was passed in. And if we look at the 4 values passed into our singleton list, each one of them invokes the constructor that takes 2 parameters, an integer and a string. So the CanID for front left drive is 11, and its string location is front left. The CanID for front right drive is 12, and its string location is front right. The CanID for rear left drive is 13, and its string location is rear left. And the CanID for rear right drive is 14, and its string location is rear right. So this class can be very useful for initializing and making use of your motor controllers when you start building an FRC robot. In our next Java class, which is the FRC Java class, we're going to go through a couple more examples of how we use the WPI FRC Java library and how we put it together using enumerations and using encapsulation and abstraction and inheritance. So this pretty much sums up the control flow statements for the introduction to Java programming. Hopefully, you're starting to get more and more out of it as we get deeper into the introduction to Java. I hope to see you next time when we go into inheritance, which is another one of the core principles of object-oriented programming. Thanks for watching.